Our first theorem in this section is to prove that congruence modulo m is a notion of sameness on the set of integers. That is, it is a equivalence relation. You actually kind of already know this. In particular, congruence modulo 2, that is the number 2, is what we call even and odd, right? If two numbers are congruent modulo 2, they have the same parity. So if they're sort of congruent to the number 2, or if you like even the number 0, they're what we call an even number. That is, they're divisible by 2. And if they're not, they're an odd number. And any rate, you've seen an instance of this before. We're going to prove it in general for any natural number m bigger than 1. So what do we need to do? We need to show reflexivity, which you'll do. So you'll do this one. I'll have you do this in class. We need to show symmetric, which you'll do. And we need to show transitivity, which I will do. Just because it's a little bit more involved. It's not, none of these are necessarily hard at all. It's just playing with the definitions. A lot of algebra is understanding the definitions and being able to manipulate the definitions, at least when you start out. So it's not that transitive is necessarily harder than the other ones. It's just there's more variables going on. So let's prove transitivity. So what do we need to do to prove transitivity? We need to suppose we have A, B, C, and Z, and A is congruent modulo M to B, and B is congruent modulo M to C. And here, this is why I like this notation. All of this fits on one line, and I write big and chunky. But if you want to use the other notation, that's fine too. Now we're going to write out what both of these, I guess we should write out what we want to show. We show A is congruent modulo M to C. All right, so that's what we are assuming and what we want to show. Now let's write out what we're assuming. That is, we're going to write out what these symbols mean. So since A is congruent modulo M to B and B is congruent modulo M to C, M divides A minus B and M divides B minus C. Great. Now, A minus B plus B minus C is equal to A minus C. And let me just put this in a sentence. So notice that A minus B plus B minus C is A minus C. And you proved that divisibility satisfies this 2 out of 3 condition. That was one of the problems in class. And in particular, we know it divides this one and we know it divides that one. So therefore, it must divide third. But M dividing A minus C is exactly saying that A is congruent modulo M to C. So that's certainly one way of going about this proof, and that's the end. That's what we want to show for transitivity. There's another way of going about this proof, which is a little bit more, I don't want to use the word painful, but that's what comes to mind. We can be a little bit more specific about about divisibility, I guess is what I want to say. So alternatively, we're going to start at star up here. So we're going to redo star. We would say since A is congruent to M mod B and B is congruent to M mod C, we know that M divides A minus B and M divides B minus C. And then the definition of divisibility, there should be some K and L such that what, scroll way down, Well, A minus B is Km, and B minus C is Lm. Okay, so we've used the definition of divisibility. Then A minus C itself is, we can insert a plus and minus B here, and then cleverly associate. A minus B is Km, B minus C is Lm, so we get K plus Lm. And so on the left-hand side, we just use pink, we have our A minus C, and on the right-hand side, we have it's equal to M times something. Thus, we can conclude that M divides A minus C, and so A is congruent to M mod C, ending the proof like before. And if you look at this, all we've done is we've revisited the proof that you did in class on the 2 out of 3 property for divisibility. But nevertheless, in class you'll show that this relation is reflexive. That's very simple. It's symmetric. That's also very simple. And then you'll do these two, and then we just did transitivity, so it is in fact an equivalence relation, and that completes the proof of the theorem.